If you have ever wondered how a flood wave changes shape in a channel as it travels downstream and why it slows down, flattens, or arrives later, the Muskingum method is the tool that explains it. In this video, we break it down from the ground up. First, we uncover the storage relationship that makes Muskingum method so powerful. Then we turn the theory into practice with a clear step-by-step numerical example that you can use in your projects or assignments. Let's get started. The water surface in channels is sloped and storage is influenced by both inflow and outflow. Storage in channels can be approximated by combining two storage types, prism storage and wedge storage. The prism storage is related to the output and is shown as KQ. The wedge storage, however, relies on the difference between inflow and outflow and can be calculated as Kx multiplied by I minus Q. We call this equation 1. In this, K is the proportionality coefficient and is associated with travel time in the reach. A larger K results in more attenuation, which gives a flatter hydrograph. X, however, is a weighting factor, a weight of inflow versus outflow. This parameter controls the balance between inflow and outflow storage. X generally varies between 0 and 0.5, where x equal to 0 represents a linear reservoir, where storage is a linear function of Q. In the presence of observed inflow and outflow data, K and X can be found through a calibration process. However, in most cases, the outflow data is not available and we need to estimate K and X. In this tutorial, we will focus on the case where outflow data is not available. For X, the recommended value in such a scenario is 0.2. K, on the other hand, can be estimated by K equal to L over C, where L is the reach length and C is the flood wave celerity. C can be approximated by multiplying 1.7 by the average velocity from Manning's equation. Now let's bring in the continuity equation. The change in storage ds over time dt is equal to inflow minus outflow. The discrete form of this equation will be like this. Let's call this equation 2. The target output in a channel routing problem is the outflow Qt, where inflow hydrograph parameters K and X and the initial outflow are available to start with. So let's build an equation to calculate it. First, we rearrange equation 1 to this form. Using this, we can write a storage expression for the two time steps t and t minus 1, like this. Now let's replace st and st minus 1 in equation 2. Since Qt is the target output, we will bring all Qt terms to the left side and bring all other variables to the right side of the equation. This gives us Qt as a function of other parameters. As you can see, the delta t in the denominators can be cancelled. Then we can divide all terms by 2k multiplied by 1 minus x plus delta t. Then we will get Qt as a function of all other variables. We will call these multiplying brackets C1, C2, and C3, and we will get the Muskingum formula for calculating the outflow. To have a stable calculation and avoid getting negative values for Q, the following criteria need to be satisfied. First, the summation of C1, C2, and C3 should be 1. Secondly, the delta t, time step, should be between 2kx and 2k1 minus x. There are also some recommendations for the suitable delta t. For example, it is suggested to keep delta t smaller than the time to peak of the inflow hydrograph. Some studies recommend delta t being smaller than 1/5 or 1/6 of Tp. Well, it's time to solve a numerical example. The inflow hydrograph at point A of a reach is given. We want to find the outflow hydrograph at point B, which is 12 km downstream of the first point. The flood wave celerity is given as 3 meters per second, while x equal to 0.2 is adopted. The initial outflow is assumed to be 0, and as can be seen, the provided inflow hydrograph has a 1 hour time step, so our delta t is 1 hour or 3600 seconds. In step 1, we calculate k using the formula that we had, k equal to L over C. Our L was 12 km or 12,000 meter divided by C, which is 3 meters per second. That will give us 4,000 seconds. Step 2, we check the delta t requirement. For this, we need to satisfy delta t being between 2kx and 2k times 1 minus x. If you remember, our delta t was 3,600 seconds. If we replace x of point 2 and K of 4000, we can calculate 2Kx and we will get 1600. Similarly, the 2K times 1 minus x will be 6400. As can be seen, our delta T falls between 1600 and 6400, so we are good to proceed. Step 3, we need to find C1, C2 and C3 and check the next criterion. If we replace Kx and delta T values in the given equations, we will get our values. C1, 0.2, C2, 0.52 and C3, 0.28. As can be seen, the summation of these three is 1 and we satisfy the next criterion. Step 4, we start the tabulated calculation of outflow. For this, the first two columns are dedicated to the inflow hydrograph, time and inflow values. Considering the Muskingum equation, we allocate the next three columns to the three terms of this equation. Finally, the last column will be for Qt, our desired output. For the first row, we can only fill columns 3 and 6 since the inflow and outflow values from previous time steps are not available, and we'll leave them empty. Be mindful that the given initial outflow of 0 sits in the first row. The actual calculation starts from row 2. C1 times inflow 5 give us 1. C2 times previous inflow 0 will give us 0. And C3 times previous outflow of 0 will give us 0. Now the outflow will be the summation of columns 3 to 5, which give us 1. Let's do another row. C1 multiplies to inflow 12, give us 2.4. C2 multiplies to previous inflow of 5 will give us 2.6. And C3 multiplies to previous outflow of 1 will give us 0.28. Our outflow will be sum of the 2.4, 2.6 and 0.28, which will be 5.28 cubic meter per second. As you can see, this process can be easily facilitated in Microsoft Excel. So let's bring the rest of the calculation there. Well, to start the Excel calculation, I've already provided delta T, X and K values as we explained it earlier, and also C1, C2 and C3 are calculated using the available formulas. I've also plotted the inflow hydrograph to just have a visual inspection of it. So you can see the peak value happens at 6 hours and the value is 93 cubic meter per second. A reminder that our Qt, the initial value, was also given to us. So the initial value for Q is 0. And also because of having the first inflow value of 0, this cell is also going to be C1 multiplied to 0 and will be 0. The other two cells, as we explained earlier, they are going to be empty. But here, because I want to plot it later, I have put zeros in them. I start with the row 2. So here, my calculation starts with multiplying C1 into the inflow value of that row. But before I finish it, I add $sign in order to fix the cell related to C1 value because I want to drag it later. And similarly, for this one, I go to C2 multiplied to the previous inflow value, which in this case will be this cell, 0, C10. And similarly, I add $sign. So I add $sign here. Done. We go to the third one. This is C3 multiplied to our previous Qt, which is this yellow cell here, G10. And I will add $sign as well. So with this, we have completed the first row, and following the Muskingum equation provided here, I just need to sum up the three values that we calculated in columns 3, 4, and 5, and that will give me the Qt. So the rest of the process is very easy. I just bring and drag it down all the way here. And I have already built in the outflow hydrograph, so it's now presented here. One point that I want to highlight is the fact that although our inflow finishes here, becomes 0, we can continue the calculation perhaps for more cells until our Qt converges to the 0. So for example, here I would stop. It's like 0.04. And the reason of that is if you look at the Muskingum equation, out of the three terms, the first two have I in it. So when I becomes 0, gradually those terms become ineffective. but the QT minus 1 is there, and still we can produce some QT for a couple of time steps until we converges to 0. So with that, I just add some numbers here in order to complete the hydrograph. So I've already selected the values into the diagram previously, so you can see that now I have the full picture. So now two things, attenuation and translation. You can see that the peak is shifted towards the right, and the attenuation also has happened. Our peak is smaller. So if we compare the peak values, the inflow peak is 93 cubic meter per second at 6 hours, while our peak in the outflow happens at 7 hours, and the value is 84.97 roughly, which is smaller than 93. It is worth mentioning that in the linear reservoir, the peak of outflow generally falls on the recessing limb, but in the Muskingum method, because the storage and discharge have variable relationships, the peak is not situated on the recessing limbs. Another point that I want to check here is a quick sensitivity on the K and X variables. So if you remember, I mentioned that if I increase K, I'm expecting to have a more flattened or attenuated outflow. So let's increase K from 4,000 to 6,000. You immediately see that the peak's actually falling down, so the value now is 78.95 and also a bit shifted. I bring it back, and the other point is about X. We had the criteria of having X between 0 to 0.5. I purposely want to choose something out of that range, let's say 0.7. What is happening is that you can see that there are a lot of negative values for QT, which is not desirable, so it's better to keep it within that range. So now you have seen how a channel routing method like Muskingum models both translation and attenuation to transform an inflow hydrograph into a realistic outflow. In our next video, we shift from channel routing to reservoir routing. We will walk through a complete hands-on tutorial of level pool routing, another essential tool for flood modeling, reservoir analysis, and retarding basin design. If you want a full picture of how water moves through a system, don't miss it. Thank you for watching. See you in the next one.